Okay, so today we'll talk about how the learning theory can be applied to biology. Now, why this would be useful? Well, from 2 points of view. So it's useful because we can try to model biological phenomena using the mathematics of learning that we've been developing. So it's a help to biology. And the second, we can, once we do that, and once we identify the relevant description of biological system, we can take it other way around and say, all right, now let's take biological algorithms and apply to machine learning. There are many examples of that. One we discussed is when we identify the biological phenomena of program death and replications, try to see what it's useful for learning algorithms, but there are many others. So let's get through this, try to see what happens in biology. Now, I'll argue that biological systems are actually a lot more complex, and they have some things that are not usually present in the learning system, deep learning systems, but nevertheless, that's the good news because we can learn a lot from that. Okay, so to view organism as a learning system, either one organism or a group of organisms or single cell, whatever level you are trying to look at any level, you can try to identify we should first try to identify what you're going to call trainable and what you're going to call non-trainable variables. Now, even if the exact architecture, how things are connected, isn't clear, it's useful to have that distinction. But for biology, it also turns out important to not only identify those two degrees of freedom, but to identify subcategories. Now, for the trainable variables, the division will be in the three subcategories. Core variables, something that just describe, say, a given organism, but do not vary when you go from organisms from the same type to the organism of a different type. So we'll call them core genotype variables. Then there are the ones that do change. Now, whether something changes or doesn't change depends on the time scale you consider. And so we'll talk about that. But let's say we fix the time scale and we observe that some trainable variables do change. They are adaptive. An example is phenotypic variables. And the third one is they might change, but they do not, they change in their values, but they do not change their loss function in context of learning system, or something that we'll describe as a fitness function that is usually used in biology. We'll draw a link between the two on the following slides. Okay, so something that doesn't change, yet it's called trainable because if you consider different scales, the time scale, they will start changing. Something that does change on the constrained time scale, adaptive, and something that, although changes, doesn't lead to changes in the loss function. And then there are two types of non-trainable variables, the ones that are associated with the organism itself that describe it, and the ones that are associated with the environment, right? So this is, we already seen before, the organism we should think about as a bulk degrees of freedom over neural network, in the neural network language, and environment is the boundary. And the idea is that they're, of course, interacting with each other, but there is a separate distinction, what you call the environment and what you call organism. So those are the 5 things. It turned out that if you just take the first letters from the description of those variables, then you'll get a word canoe. And also, if you go from up to down, this is the actual frequency. This is the direction in which the variables are changing more and more. So cores don't change at all on the constrained time scales. Adaptive do change. Neutral change a lot more, but they are irrelevant. It's like flat directions. They can run left and right without changing the organism's behavior. And then you have non-trainable variables of organisms, which still change on even of small time scale, so it's change faster. And the fastest is the environment. Environment is evolving all the time. That's the model. So that's the model. Now we haven't specified a loss function yet, so let's get there. Now, we already seen before that the bulk loss function can have two parts, something that I refer to as kinetic and potential terms. In context of biology, the minimization of this kinetic term is ability of the organism to predict its environment. So if it's a good in predicting an environment, it has a good internal model of the environment, then its loss function is small. Again, we'll connect it to the fitness function, meaning if an organism is able to predict environment, it's more likely to survive in the given environment. I will be always drawing a connection to the previous lecture where we discussed autonomous particles, because that is a concrete microscopic model of something that has many similarities to biological systems. So taking that model, a model of autonomous particles, and generalizing it to include more and more biological features is a rather straightforward exercise. So I'll be referring to that model a lot. So for example, the avoiding collision terms that we had before, you avoid collision if you're good in predicting what the other particles, autonomous cars will do. And so that is related to the kinetic term in this sense. And the other term is a potential term. It's a more global term. You're not just thinking about your local environment. You're thinking about where you want to go, right? So the organism may want to go to get food, or the organism may want to go to reproduce. And so that would determine the loss function as well. And so that is similar to arriving to destination term that we discussed last time in context of autonomous particles. So to go back now and to have a more precise mathematical definition of the three types of trainable variables, what we should do is to look at the derivative of the loss function with maybe other terms with respect to trainable variables. Now, so think about the first derivative with respect to trainable variables. Near equilibrium, the system would tend to go to where the derivative is zero. So it would minimize the loss function, but there still can be different second derivatives. And if the second derivative is very, very large, then not only the system would remain near zero, it wouldn't want to move away from it, because any motion to the left or right would cost a lot of loss function. It would increase the loss function dramatically. And so those variables will remain where they are. They will be staying in that minima. In physics, we call such degrees of freedom are very massive. They don't like to change where they are. And so that happens when the second derivative is large. Now, when it's small, then it's adaptive. So really, you can still go in those directions, and maybe you can discover even better minima. And so those are directions that are most useful for learning and exploration of the landscape of the trainable variables. And then there are the ones that create no change to loss function. They're neutral directions. Things can go left and right in that directions without actually contributing much to the changes in loss function. There's a flat direction, symmetries. We've had many words for that, and so we'll use it neutral variables. Mainly coming from the fact that in biology there is a term of neutral genes, something that is related to that type of variables. Okay, so now let's talk about organisms. And I already mentioned that we will be describing biology at different scales. So we just take a scale of the organism and say, and now when I go through and describe what all those things mean in context of learning theory. So we have a organism scale, the state of organism described by XO. Now this is the state of organism with respect to environment, and then the biological traits are the ones that are equivalent to the trainable degrees of freedom. So the biological system trying to adjust them on that particular scale of the organisms on which we observe the organism, and that's what the training is. Now in the autonomous driving model, there were no replication, and I will talk a little bit about that on the next slide. So do not think about this as literally the loss function of organisms. This is just an example of things that we can have there. And this is again analogy from physics. When we write down some Hamiltonian or Lagrangian, we don't say, well, this is the Lagrangian or Hamiltonian that describes the universe around us. It says, well, let's play around with a toy model, what this looks like, and then we'll be adding more and more phenomenological terms as we learn how the given physical system evolves. In this case, construction of a biological model would be equivalent to writing down the loss function with all the terms that should be there, even if they were not there in our simplest toy model that we started with. Okay, so I'll take questions after the next slide, but let me now go through this description of organism all the way. And so I already mentioned that fitness function is something that is usually associated with a given organism. Usually the way it is defined is the reproductive success of a given organism with a given phenotype. Now we're going to dig a little bit deeper. So we are saying, yes, reproduction is important, but you cannot have reproduction if you cannot find the food or a suitable environment for you to reproduce, or if you cannot predict the environment or avoid dangerous situations. So we are really saying that potentially there is more to the story of what is actually the microscopic description of fitness. And so here, this is what I write here, and I've kind of already mentioned it before. Even taking our simplest autonomous particle model, we can generalize it to include everything that describes usual organisms. So we can add like reproduction terms. So our autonomous particles can not only it can be two types of them, male, female, maybe they collide and then they produce an offspring, or different degrees of complexity. We can increase this model with arbitrary new terms that would describe model better and better a given system. What is important to note that since we're mentioning here autonomous particles, is that those particles from the previous lecture, they were completely independent. They were separate neural networks that learned how better behave in the environment, how better to drive. But presumably we can have them having shared degrees of freedom, so that there's certain things that they learn independently and certain things that they share between each other. So if one particle learned the, say, right hand driving rule, it will be transmitted to the other particle, and the other particle would know it ahead of time without having to learn it. So those shared degrees of freedom, by whatever method they're being transferred, is something that, again, we can add to our numerical model, and that would reproduce better of this core genotype that describe what a given organism is, and something that all organisms of given type learn. However, what's important to note that the fitness as a defined in biology doesn't have just the right properties. And so to make it having right properties, we actually have to take a log of it. And then it would, to write properties with the point of view of the loss function, it has to be additive. And so if you have two organisms, you should have the twice as much loss function associated with them. And so to have that property, you should take a log of phi, and that is sometimes called as additive fitness. Not only that, and of course, minimization of phi or maximization of phi, usually in biology, they want to maximize fitness. So maximization of phi would be equivalent to minimization of negative log phi. So, but I add an extra coefficient here, t, and at this point, it is just some parameter, because if you multiply your loss function by arbitrary constant, the minima, a local minima, would not change. Whatever was minimized before will still be minimized after you multiply by a constant. So at this point, t has no interpretation, microscopic interpretation. It's unimportant. We also discussed that this coefficient can always be observed into the learning rate and kind of rescaling your time scale. Not very important. But as we'll argue, this t is very, very important at the level of statistical description, and it will actually play an important role. Its inverse will be Lagrangian multiplier that imposes a constraint on the average loss. So, and this is very important point, because in biology, the sometimes people who do model statistically, they sometimes associate with temperature something else, something that is not related to the Lagrange multiplier, and that's a mistake. So we'll show exactly what that happens, and so there's nothing else to the temperature in this description but as inverse of Lagrange multiplier. Okay, so other questions about this first 3 slides of how we want to model organisms using the learning paradigm. Okay, so let's, Vladimir, you had a question?
Yeah, so you mentioned the additive fitness. So is the loss function then defined over all the organisms together, or are you still optimizing each one separately in the environment as they interact?
Good. Yeah, so we'll actually get to that momentarily. You always specify a scale on which you want to study it, and the scale can be loss function for a single cell, loss function for the collection of cells, loss function for the organs that are made out of those cells, loss function of a group of organisms, loss function to the entire biosphere. So all those are different scales. And actually, this is, you anticipate my next slides. And on every single scale, you can say, well, I want to know what the loss function, and I want to see how on that scale the system would evolve. Okay, and you can ask it on any scale. Okay, and so, and then presumably what's happening is that the cells are optimizing, and we call it frustration. So sometimes, so the cell tries to optimize its own loss function, but at the same time, the cell is a part of the organism, so it is indirectly optimizes the behavior of the entire organism. And so basically studying all those different scales is first specifying the scheme, then writing down the function is equivalent to coarse graining. Like, what do you want to pay attention to? What you want to integrate out? What is the chosen scale? It also is related to what you really want to call, core non-changing variables, adaptive changing variables, or neutral changes variables. And this division into those 3 types of variable will change depending on what is exactly your study, or in other words, what is the considered time scale. Okay, so this is the example. Go ahead.
Like again, why we need log?
Oh, log, just to have a trait property of being additive. So if I have twice as many, organisms, I want to have fitness, double. Well, I want to the thing that describes loss function, I want it to be doubled. Now approximately. So if you don't have that property, then this cannot even qualify. It just has no hope of being called a loss function. So additivity property is important. Yes. Okay, so let's move. Yeah, so and that's the idea, right? You choose the time scale. You choose system. You look at the system and you say, okay, if certain things don't change, I'm going to call it core variables. Certain change, I'm going to call them adaptable variables. And then the others are just not trained at all. They behave as if they were non-trainable degrees of freedom for the considered time scale. And so that's the idea of this multi-level learning. So let me reiterate the same thing once again. Everything, the crucial part is the time scale. So they can be a time scale of the lifetime of an organism. They can be a time scale of the time of the group of organisms, lifetime of a single cell, and all those are different time scales. And by changing time scales, the very same variables will distribute themselves between different meanings, what they care. And this is what we call multi-level learning. In biology, some similar context, people call it multi-level selection, meaning that the very same things that happen on one level will also be happening on the other level, but they may have different names. But the idea of this is we say, well, everything that happens on one scale, every single phenomenon that happens on one scale will be happening also on the other scale, but it will just have a different, may have different name for it. But the idea, if the fundamental principles behind it would remain the same. Now, in physics, so before we go on to biology, again, there is this notion in physics, very well, again, for people who are familiar with the physical construction of physical theory, know very well that if you say about, to describe a physical system, you have to write down the Lagrangian, and the Lagrangian has some constant in it, and like, mass parameter, coupling constant, and people would ask, what happens with the very same system if I start looking at it at different scales, at different energy scales? Well, it turns out for many systems, what you have is that the form of the Lagrangian would not change, but all of the constants will change. They will run with a scale. So basically, the basic principle described in the system may not change, but the exact phenomenological model describing the system at different energy scales would change. This has the name of the renormalization group, and basically the idea is that happens because whenever you probe a system at a given energy, what you do effectively, you integrate out the degrees of freedom that are irrelevant for you, and then by integrating out, you actually change what you effectively observe. But to do that, you have to specify a scale. You say, well, I look at myself at the system at a given energy scale. I look at the system at a given time scale. And then everything that goes too fast for that time scale, you take a statistical average over it. And everything that goes much slower than the considered time scale, you just consider it as being a constant. And so here it is. Some variables are just constant, core variables. Some variables that goes too fast, that can be non-trainable for you, degrees of freedom, you can just integrate them out. And the others that are changed on your considered time scales, and there can be adaptable variables or neutral variables. Those are the interesting ones. Those are the ones for which you have to pay attention to on the considered time scale. And so this picture here illustrates that basically you have the same network of some connections of how things influence each other. And then depending on how you change your time scale, the red degrees of freedom become green, and then even a larger time scale, even those that were completely also red can even become blue in this picture. What it means that on the small time scale, these reds were all considered constant, that they don't change. But as you increase the time scale in which you observe, they start changing. And so they become green, maybe this adaptable or neutral variables. And if you take even larger time scales, then some of them, or more and more of them, will move into the direction of green and blue. And other way around, if you move from right to left, things that were changing very fast, like blue, and were considered as part of the environment, something that you can integrate over, like your boundary conditions in context of learning, boundary dynamics. Once you start paying more attention and consider a smaller time scale, they may be the degrees of freedom that you really want to pay attention to. And so that goes both way again. So it makes no sense to say I have a biological system and I model it unless you specify what is the time scale in which you model it. And the things that do not change on one time scale may change very much on some other time scale. Other questions with respect to multi-level learning? Okay, so now one more thing I'll add. We did the fact that all the time scales matter, and then really describing which time scale you want to look at. We had evidence for that in the discussion of self-organized criticality, where we saw that different time scales, a wide range of time scales, is important. Now, if it would not be the case, if there was only one time scales for a given learning system, which is important, then we would have concentrated on that time scales, and everything would have been solved. There would not be this. There wouldn't be that hierarchy of scales. But in biology, we do see evidences that does happen. There is a learning that happens at the level of cells, There's a learning that happens at the level of organisms. There's a learning that happens at the level of the group of organisms up to the entire biosphere. That's something that, again, not quite implemented in the machine learning algorithm, other than this autonomous particles model, where you can add the missing parts from biology, but it already has at least one scale. It has a scale where you have the different autonomous particles moving around. But then you can say, well, let's consider let's modify a loss function so that those autonomous particles start forming groups of particles, and then groups of particles, and then there will be some kind of criticality in the behavior of all these autonomous particles. So that seems to be advantage from the point of view of learning on different scales. Okay, so now the two things we've covered so far. So we described what organisms are, how they relate to things in biology. Then we discussed that, well, actually, hold on, you cannot really study biology unless you specify a scale. It's okay to study any scale, but you have to specify time scales. Now, what we're going to do that, now we're going to pick a scale, and a given scale, see how now we can use the learning theory to describe and make prediction of how the biological system would evolve. So for that, we need statistical description, and just like statistical description of the machine learning system that we developed a few lectures ago, we'll be able, since we're able to construct a loss function, we can just borrow all the machinery or statistical mechanics to evolution. Now, the idea there was to integrate out fast changing degrees of freedom. And so in this context, we're going to call those fast changing degrees of freedom the non-trainable variables. We integrate them out, but we keep track what the average loss function is. And that will give us an idea of what the fitness is. But this connection will be made later. So this is just to remind you how that works. So yes, you start always with a loss function, then you set a constraint on the average loss function, and then you have these two types of variables, the ones for which you pay attention to, and the other ones that you don't pay attention to. And then according to the maximal entropy distribution, it should be this. We also called it canonical ensemble. This is a distribution of those fast-changing variables, non-trainable, for fixed trainable variables. So this is the distribution. And then this thing that turned out to be very important is a partition function, is the integral of x. Now it only depends on this trainable degrees of freedom. Now, as we'll argue what follows, that this is actually what related to the what is related to the fitness function. And as you can already kind of see that you've exponentiated here. So taking a log of z is something that we call free energy, and it does have the right properties of the loss function, but the macroscopic loss function. The one that something that needs to be extremized. Okay, so in this statistical description, we still have the notion of free energy. We have a notion of temperature, average loss, entropy, and so on. Fikra, go ahead.
Yeah, so which one of these variables has the time variable, or
yeah, so time scale, right? So here, the x is changed very, very fast. So you consider them at the level of statistical ensemble. So everything changes, all variables change. But some change very, very fast, and so you consider them at the level of statistical ensemble. Some things change slower, so you monitor their changes. And some changes, things don't change at all, which are not even written here. Or maybe part of Q, something that's really, really frozen.
Okay, so they're like it's not included in a obvious way, like it's part of the variables.
Well,
I don't see the time.
as obvious as it can be, right? So this is the variable. So x contains very fast changing variables. It's like
okay.
So x are the fastest changing variables. Those are the I call the blue, or the environment, or non-trainable variables organism. Something that changes all the time, like for you, right? So every information you receive from the outside world changes very fast with very high frequencies. Compare it to things that you learn. Those are change on the slower time scales, and this is the time scale that you're considering. Learning happens on those time scales, but what you're learning this.
So on larger time scales, do the x variables drop out of the equation, or what is happening?
So as you increase the time scales, x's, there's more and more x's. There are more and more of the non-trainable. You're starting to treat more and more variables at the level of statistical ensemble. So as you increase the time scales, if you take very large time scales, then everything is just statistical ensemble. Okay, so then all variables will just be blue. And if you consider very small time scales, everything you're kind of doing microscopic analysis, and you like follow the evolution of every single molecule, and there's no more statistical ensembles. So this is just the idea. And it's again, this is not new to biology. This is how physics is done. We can never monitor all variables, and we always have to divide on those three things. Some things we just say it doesn't change during my experiment. This is constant. Some things that we are only treating at the level of ensembles, so they change too fast to monitor, and so we say they're equilibrated. So constant, equilibrated, and in between is what you actually monitor. So this is not unique to this setup. This is what we will always do.
Okay, thank you.
Okay, so and of course, once you have the statistical description, which requires you to write down what h is, loss function. But we already said in the discussion before that sometimes you do not know what h is. You still want to figure out what f is, and then you do it. You can do it at the level of thermodynamics, where you say, well, wait a minute, let me just calculate from the experiment what u is. U as a function of entropy. So in this case, an entropy of non-trainable variables as some trainable parameters. And then this would be your first law. So f has to go to some saddle point where this is extremized. Now, whether it is minimized or maximized with respect to q also depends on how much of the trainable those parameters are and how much of the chaotic they are. And that's but either way, you would get to equation of the first law, where this du describes the change in the loss function, TDS describes kind of environment, and this is describes of the trainable part of your system. You can take it a step further. You can also not pay attention too much to the individual. And in this description, U has to be modeled as a function of S and Q. And in this thermodynamic description, you have to introduce the biological temperature. You can introduce biological temperature. By how much your loss function changes, or the log of the fitness changes as you change the environment, right? So make the environment more complex. Now, presumably, it will be harder for the system to be in that and to survive in such an environment. And so you can perform experiments when you complicate your environment, make it, maybe just adding the physical temperature to this and see by how much the loss function changes. So at some point, du can just drop to zero because, or to go to infinity, sorry, so because this organism cannot survive in such an environment. And so that would correspond to a huge biological temperature. You increased entropy to large enough, and so then all of a sudden it's no longer possible to survive in that environment. But you can do it gradually and kind of study the behavior of a given learning system, of a given organism type, different environments. So the point here that you do not necessarily need a microscopic model of your biological system. You can just approach it phenomenologically and say, right, let's just study how things change in different environments. Now, you should also, those cues may be just the genotypes, right? So some you can obtain them microscopically, looking at your sequences, but DNA sequences. But maybe you can say, right, I don't want to study it that microscopically. Maybe I just want to, how many count how many variables are important, how many variables, trainable variables, does a given system has. So some systems may have a lot of trainable variables because the algorithm is very complicated. Others may have few variables because and their genome sequence will be shorter. And moreover, in these sequences, the adaptable, the relevant variables that are learning will be smaller. And then you can ask a question, okay, so let's say we have given organisms and it is in some state, equilibrium state, and then it's trying to recruit a new degree of freedom, a trainable degree of freedom, how difficult it is for it to do that. Now, usually it's not very difficult because there are many, there are many directions that are not adaptable, and so they're neutral. And so you can take a neutral direction and say, okay, well, now remember something important about the environment. But sometimes you don't have many available, and then this would correspond to having very large mu. It's very hard for you to recruit a new degrees of freedom, trainable degrees of freedom. And then that's the, and again, you can look microscopically and study your genome sequences, or you can say, well, let's just see what happens, how the system behaves, and let's study how the system behaves, how many. So we will connect this K to the number of organisms in the following slides, and then just by observing how the number of organisms changes through a very long time, you can kind of understand how the number of relevant degrees of freedom changes. Okay, so first we started with a very microscopic model. You really have to model it very well. It's like redoing the autonomous particles simulation, but with more terms, with more complicated interactions, and then you can perform this integral and create a conclusion. Or you can say, well, forget about all that. Let's just do it phenomenologically. Let's just extract, observe how the learning system changes as I change its environment, and then you would be able to reconstruct this function or that function. So now let's move one step up and consider now a population of organisms of the same type. So instead of looking at the individual organism, like what was most of the time we're doing so far, because of this multi-level learning paradigm, we can look at it at any scale. So let's look at the population of organisms. So if you look at the population of organisms, what we want to say, let's only choose organisms of the same type. And so maybe they will all have the same number of genotype variables QC. So the core variables will all be the same. They'll all be describing the same organisms. That can be organisms like us, humans, or it can be organism like COVID virus, right? So they all have distinguishable presence of some sequences that can be by which we can distinguish them and say, well, yes, this genome belongs to the COVID. The reason I give example of COVID is because of some of the experimental results that I'm going to show you later. But also viruses are less complex, and so you can study their statistical or thermodynamic behavior better. And once you study how they behave, how they adjust, and to changing environment, you can infer from that what is it that you have in their algorithm, biologically, an algorithm that is useful for developing a machine learning algorithm. So it works both ways. So we can model it as a learning system, or we can borrow from their algorithms to do the learning that interests us. Okay, so the setup here, you have a group of organisms. They have some fixed core variables which describe those algorithms, and then they have a number of adaptive variables, and that number can change because they can borrow the degree of freedom from the neutral variables. Now, there are usually two interpretations of probability theory: Bayesian subjective and frequentist or objective interpretation. Now, and this works well when we have many organisms. In our case, we actually and they're the same if you have many attempts to perform your experiment where the probabilities are involved. In our case, that's not the case. We have only a finite number of organisms. And what we're going to assume, this is the assumption we're going to make, that the number of organisms is exponentially large with the number of the trainable variables, adaptable trainable variables that organisms have. Now, the reason for this is quite simple. Now, if you had more than that, if you had more variables, trainable variables than that, then so the right-hand side would be much larger, this exponent, then most of the variables would not be learned, right? So you would have too many. If you have, if your number of organisms is too larger than this, then most of the variables would not be learned. We just have identical copies of the organisms with exactly the same set of trainable variables. So you would not be wasting resources from the point of view of learning how the organism behaves with the different sets of parameters. So that's not good. And the opposite limit, when you have too few organisms, not as large as that, then it means that those organisms, again, are not learning all of the variables that they have. And then again, effective K would be smaller. So that's the idea. And that relates kind of, then you can just observe organisms in your experiment, number of organisms, and say, all right, I know how many variables, trainable variables, they're using to adapt to different environments. And so then by observing how that number changes, you can deduce how many trainable variables are being used in any given moment of time. And then if you do that, you can observe the number of variables changing. You can keep changing the environment and reconstruct the function like this. Now, the reconstruction of this function actually comes not from writing what U is, but by doing this. So let me get to that. So basically, what you will be reconstructing, you'll be reconstructing the Legendre transform of UK. But we'll get to that shortly. Okay, so that's the setup. Let's set up. So now you have a system. It's system population of organisms, and you're changing environment, and you see how the organisms adapt to this. All right. Now there is a model to this, which is called an ideal mutation model, which makes certain assumption that we're going to now discuss. So they assume that you have a number of organisms that described by some collection of the genotypes. So those are like, you can think about them as the adaptable variables. Those are the variables that distinguish about what is organism at this moment of time. Now, however, this model has one interesting feature. So what it's saying that this ensemble of organisms undergoes rare mutations. So the Q1 changes maybe to Q2 on some time scales. And after that, there is a fixation, meaning that all organisms in this ensemble will become of the type Q2. So you had all of them of Q1, then you had all of them of Q2, then you have all of them of maybe Q7. And then on those larger time scales, they keep going, right? And then the system comes to some equilibrium where, as a probability distribution over time, ensemble average, it undergoes through all those different states of Q. Okay, so now we're going to describe this model using the loss function. And in our language, in order to deduce the result that people obtain, we have to make an assumption that the organisms are not interacting. And so the total loss function is just the sum of the loss function of separate organisms. So that's the only assumption you make. And if you make this assumption and you integrate out all this information about the environment for each of them, you obtain a function of that type, where you'll have an exponent times minus beta ME. And here, this is f of q. F of q is the free energy of a single algorithm, single organism. So that's the result, and that only valid if we assume this. So they're not interacting. Yes, they all share the same Q, because of the fixation at any given time, but each organism is not interacting with one another. And then basically the ability of a given organism to survive only depends on itself. Then you get this result. And so what people did when they look at this formula, they associated with NE as inverse temperature. And that's, of course, a mistake because inverse temperature is not NE. Inverse temperature is inverse beta. Inverse temperature is the inverse of the Lagrange multiplier that imposes the constraints. Now here, for this simple model where the organisms not interacting, they kind of come together, right? And so it is understandable that you can move what you call T either here or anything in between, move part of it to the left. But as you start increasing the complexity of your model and organisms start interacting, so you add other terms to your loss function, then there is no, it's very clear what beta is, and it has to be Lagrange multiple. Okay, now you can take this model, this distribution, and rewrite it this way, where it is, where now Z, or a partition function, is e to the minus beta f. So I've just took e to the minus beta f, moved out, and NE moved to the power. So now it's clear that whatever we call the partition function of single organisms is playing the role of the fitness. So partition function, something that biologists don't discuss it. It's actually a macroscopic counterpart of the fitness. Remember, we called it H. We called the additive fitness because of this exponential difference between them. But it is actually the partition function that should be associated with fitness once the environmental degrees of freedom are integrated out. So if you average over your environment, then this is partition functions plays the role of fitness. And so before I take questions, let me just show you why this model is interesting. And here's a concrete prediction that it makes. So you take your system of organisms, and it has only this, each organism can be in one of those any states. Not any, it will be one of the states described by Q. And you look at the system for different environments. First, the system stays in one environment, and then you change the environment and stays in the other environment. So there are two different environments, but the system is the same. And so the loss function is the same. And so the only thing that would be different would be beta. In one case, you would have maybe higher biological temperature, lower B. In the other case, you have lower biological temperature, lower B, beta 2, beta 1 and beta 2. But if it is a system described by this loss function, then here's a prediction. When you take a log of your partition function, and recall this is a log of fitness divided by log of the partition function for the second environment, so there are two environments denote 1 and 2, then the ratio should be such that F's cancel, and the ratio becomes just the ratio of temperatures. So you take a given Q, so it's a given organism at a given state with a given genotype and two different environments. You measure how what the partition function for it, what is probability, right? Because this is partition function describes probability. And then you find those two expressions, you find them a ratio from one to another, and you see that the result doesn't depend on Q. And that is true because of the way we define the loss function microscopically. So we took a microscopic model, we did calculations, and we obtained results that now can be measured. We can really look at the organisms. And what do we mean by different environment? We can have the same, bacteria living in two setups. In one setup, maybe you have more light. In the other one, you have less light. It's in the darkness. Or in one case, you have more food. In the other one, you have less food. Or you can have, in one case, larger physical temperature, and the other one lower physical temperature. So you change the environment, but it turns out that the prediction of this would be, regardless of that, the ratio of the fitnesses for a given fixed genotype for these two environments would have to be independent of Q. And that's kind of a result that you obtain. Now, if you see deviation from that, what it means, that you have to go back and adjust your loss function. And that's, of course, how physics works, right? So we first make an assumption of Lagrangian. If physics and biology, in this case, should work, and we make an assumption of Hamiltonian or Lagrangian. We do the experiment, everything is fine, but now all of a sudden you start seeing that things are deviating from your predictions. Then what you do, you go back and you adjust your Hamiltonian or Lagrangian, depending on whatever description you have. In this case, you would have to adjust your loss function to accommodate the results. Questions? Okay.
In the context of, so it says mutations at the top, wouldn't you also need to somehow model the crossover of genes or Q variables that are learned at some point?
That would be interactions. That would be like generalization of this model. Yes. So this model is incomplete. You're absolutely right.
Okay.
So and that's kind of my point, right? So this model should not be right, and should at some point you should discover that there should be more terms added here. And if that happens, you modify your model. Yeah. So in here we don't have any of that. You just have mutations, and then everything, all organisms die out, and you have only organisms again of one type. Then you have another mutation, and again every organism dies out, but the new one, or it doesn't. And then you average over time and you get the distribution. Yeah, very incomplete. You can think about this non-interacting organisms model, like very basic, and then yet that already makes some prediction. Okay, so let's move on. So now the statement is like, yes, it will be wrong. So let's see how we can generalize it. And here's an example of how you would go about generalizing it using phenomenology. Okay, so I'm saying, well, what it means that most likely U should not be just a function of K. It should also be a function of the environment. Now, yes, this will be represented by some additional terms that you would add here, but let's not model it at the level of microscopics. Let's model it at the level of phenomenology. So here I just propose some term here that would be added. So this model is the original model. How does U depend on the number of trainable parameters? Well, it is U is the sum of the loss function of individual organisms times the number of organisms. So this is the additive assumption. Therefore, if a number of organisms is proportional to e to the bk, as we argued, there should be exponential dependence. Then this would be your form for the average loss function as the number of trainable variables. Okay, but we are saying maybe that's not enough. What it doesn't have actually the dependence of U on S on the entropy. And so maybe we should have a model, a more detailed model where U is a function of both entropy of the environment and the number of trainable variables. Here's just one proposal. I mean, there's some descriptions of why we think this may be a good model. It doesn't have to be that. It can be something else. It has some nice symmetry principles if you compare this model to the model of particles. But I'm not going to dwell on that. What it says is that let's add two things to our U. Let's first assume that it has some dependence, power law dependence with entropy. And that makes sense because we don't know what n is. So it doesn't have to be 1. It can have anything, any positive power, meaning the larger entropy of the environment is, the more complex the environment is, the harder for organisms to learn how to survive in it. And so presumably the loss function has to be larger. And the other term is this, which says that the number of adaptable variables will also grow linearly with entropy. Again, you need more variables to learn how to behave in the environment. And then they also here we propose the logarithmic dependence on NE. Well, this logarithmic comes from the discussion we had before, that NE has to be exponent of K. And then if you plug it all back together, then that's would be the form of the average loss. Okay, completely phenomenological modeling. We just had some arguments why things should depend a certain way. It was not verified analytically or numerically or experimentally, but that's the form. Okay, but once you have this form, you can perform a Legendre transform. Remember, Legendre transform, you change S to T and you change K to mu. So T would be your biological temperature, mu will be your evolutionary potential, how easy it is to add one more trainable variables to the organism. And then you can get all that. You can reconstruct it by observation of the time series of NE, how many organisms, and fitness. How do a given organism survive for how long before it undergoes again mutation and fixation. So you can reconstruct this entire function. You'll have to observe the system for a very long time. But once you do that, this is reconstructed, and then you can, argue maybe your U has this form. And now, if you observe the fitness and the number of organisms for a long time, and you get some other omega and then some other U, that's fine. That would be another phenomenological model. Now, of course, what you would want to do after that, once you obtain that, you'll want to go back and rewrite your microscopic model to have that result obtained after doing integration. And so that would be bottom-up approach. You do the experiment, you find your phenomenological function, then you get back and do microscopics. Or you can do it the other way around. You can start with adding new terms here, doing the integral, and then calculating U, and then checking it against the experiment. So that top-down versus bottom-up. Everything is fine. So before we are there any questions about phenomenological model? Because that's kind of important. That tells you what you should do if you are to study or model biological systems. Okay, so one last point that is actually makes everything much more complicated, but it's very important, and it is like the second part of the title of today's presentation: phase transition. So I will identify one new type of the phase transition that happens. So usually phase transition is associated when you have a sudden change in the parameters of the system. So you have some kind of discontinuous changes. System goes from one minima to another. And we already discussed that there will be many such transitions. There'll be a hierarchy of phase transition in the learning system. And there's nothing really unknown about that. We know that those phase transitions will take place. Now, however, here I will identify one new type of phase transition. And actually, it's important from the point of view of learning because it describes how the system develops new scales. So non-existing scales before and after in a new way. So you can think about maybe a neural network that was on your computer and it was running as one combined thing. And then all of a sudden you saw that there are isolated subnetworks that start running. And so that produces a new scale. So you had a scale associated with the whole system, and now you have scales associated with the subnetworks, weakly interacting. Or you can do it other way around. You maybe started with the weakly interacting things, like autonomous particles that had no interaction with each other, direct interactions. They didn't share any degrees of freedom, and all of a sudden, the autonomous particles, figure out that it's to their advantage to actually know to negotiate the right-hand driving rule, let's say. And so then now they all share that information, and that's a phase transition. That's phase transition from them not sharing any information to sharing this phase transition. And as I said, it can go both ways. So before they were independent autonomous particles, and now they form kind of level of society of those particles where they have some common knowledge. And you go both ways. You can start with the individual that form together, or you can start with the one neural network that goes into the discrete set of the information processing units. Now, what we believe is similar happened with in biology, and we had a distribution of statistical ensembles of the molecules that were just trying to learn, and they, each molecule we can still describe as a learning system, and then all of a sudden they start sharing degrees of freedom, and that moment of phase transition when they start sharing the degrees of freedom, when the autonomous particles no longer behave as they're autonomous, but more of having some common goal or some learned result. So that phase transition, what it does from the point of view of statistical description, it changes the ensemble. And it changes not just the minimum of the ensemble, but actually the ensemble. The ensemble before was collection of non-interacting subsystem, which is molecules, and then you have an ensemble of actually interacting. So here I say minimally interacting, and the reason for the molecules, and the reason why I say minimally interacting, well, because they're still interacting, right? So even if you look at the gas of molecules, which have no biology as we understand it, they still collide, they still affect each other, but that's a minimal interactions. They have no shared degrees of freedom. They do not have genotype variables, that core variables that describe them, this group of molecules from the other group of smarter molecules. But then we are saying, okay, what if there was a phase transition where that such a scale appeared, where all of a sudden they started having this new shared trainable degrees of freedom. But then in the level of statistical mechanics, here's what happened. Before, the correct ensemble was just tell me how many molecules there are and put a constraint on how many molecules there were. Now, after the phase transition and into the gas of organisms, you do not put a constraint on the number of molecules, but you put a constraint on the number of trainable parameters. And if you remember, there is a difference between the two by an exponential. So there's exponentially many degrees of freedom molecules or organisms, and the number of shared degrees of freedom. So there's many more of those and fewer of those trainable degrees of freedom. And that is changing the ensemble. Remember when we were deriving ensembles, we only derived it for one example when we had an average loss function fixed, and then let's derive an ensemble. You can also have average loss fixed, average number of particles fixed, average number of neurons fixed, average number of trainable parameters fixed, and you can be deriving your ensembles. What's important, what is it that you fix? And so in those two ensembles, you fix different things. And if you fix different things, the two different ensembles you will obtain. And so here's what it means mathematically. And this mathematics is only for the model, for this model that we don't even know if it is correct, but it is an example of the model, how things change with SNK. What you have is that you can have those two different things fixed, and then you can write down what is the grand canonical ensemble of molecules. That's a well-known result. And then we can write down what's the grand canonical ensemble for organisms, for those guys, which came from this expression by taking Legendre-Just formula of this expression. So you have now two ensembles. One ensemble that describes the collection of minimally interacting molecules, and the other ensemble that describes non-minimal interaction of organisms, where they already have shared degrees of freedom. And statistical mechanics tells us then if this transition took place, so at one point this was more beneficial and then was lower, and then at the other point this started to be lower for some sets of temperatures and mu's, then what we know that at the time of the phase transitions, those two things would have to be equal. And so we can just set them equal and figure out what happens, how does the temperature of the, so those curly ones correspond to physical temperature, and this mu is chemical potential, and this straight T normal T corresponds to biological temperature, and mu for evolutionary potential. So if they are set to be equal to each other, then it only happens when the the biological temperature has to be equal to a certain combination of the physical, of the biological evolutionary potential and biological and physical temperature. And so this is when the left-hand side is equal to the right-hand side. And so what it shows that if this is the correct ensemble, we have to check it experimentally. This we already checked experimentally by many experiments. Then what must have happened when the temperature, physical temperature, dropped below, then just this ensemble becomes more beneficial from the point of view of learning. That's it. So this is the simple conclusion. Just that was a good one. It was optimizing well, but now at a sufficiently low temperature, it is to the benefit of this learning system to develop this new level or scale or shared degree of freedom. Now, if this phase transition, this is a new type of phase transition, so really we changed the ensemble. If this new type of phase transition took place, presumably it can take place many times. And so I'll show you an example of the experiment where, and what it means is that once this phase transition takes place, you should see a new scale appearing, right? So a scale that describes now this trainable degrees of freedom, the new type of the shared degrees of freedom. So if this did appear, then we think it should be appearing multiple times. And here's an example where something similar appeared in the COVID. So now the phase transition, so we can also study it numerically, by the way. So you can just start with a collection of autonomous particles, drive around, they go around, and then you give them the ability to develop a shared degrees of freedom, and they start all of a sudden understanding the right-hand driving rule is more important, or maybe more. So this is just only one type of the shared degree of freedom that they would develop. But you can also do it experimentally. You just observe viruses and see how they evolve. Now, here is indirect evidence that the new degrees of freedom should be forming. It's a preliminary result. Here we have early pandemic in London, and this is a late pandemic 1 year later after pandemic. What we are plotting here is a probability distribution of the pairs of sequences versus how many distance between them. So there are very few sequences that have exactly the same genotype, exactly the same sequences. And there are more of certain type from each other, and there's very few that are very far away. So all this tells you that you have some cloud, some network of the COVID sequences, and they all have like one scale. This is the scale. This is on average how many steps. So here's Hamming distance 10. Hamming distance tells you how many characters in a sequence you should change to go from one to another. So if you change 10 sequences, you'll go from one sequence to another, most likely. But if you change, 25, it's not likely that you will observe two COVID sequences that have Hamming distance 25, at least at early pandemic. But then evolution took place, and then two scales developed. Now you have kind of some variants of the COVID that like group together, and then you have another scale corresponding how you go from one variant to another variant. And so now it's a new scale in the evolution of the COVID developed. So this is the kind of a phase transition where you don't have that scale, and all of a sudden you receive the scales. If you wait longer and we observed other sequences, you actually can see many more peaks appearing, and they describe the new additional degrees of freedom. Now, all this is the preliminary results, and as mentioned here, you should be able to see this appearance of new scales, not just experimentally directly from COVID data, but also numerically by just doing numerical analysis. I'm way over time, unfortunately, but let's see if there are any questions about any of this.
I have one, actually two.
Okay, go ahead.
Yes, if we go in with phase transitions and like relations, between like parameters, like how we can we have a network and we want to find out if there are any subnetworks.
Right, exactly. Well, connectivity. Okay, so now you're talking about different directional phase transition of when you have one joint network and then it decided to split in the separate one. So the way you should study connectivity of the network, right? Now there is a spectral property of the network that tells you that whether it's connected or not. One simple one is the energy a gap in the eigenvalues. So basically, if the network is disconnected, there should be high degeneracy in the spectrum of the smallest eigenvalue. But there may be other ways to test it. There are different ways. It's actually a good question. How do you study connectivity? How do you describe the connectivity of the networks? That's in a graph theory. It's a whole research area studying that. But yes, that's ideally what you want to do.
And second question, we are talking more about like statistical approach. Do we have some kind of formality, mathematical formality for phase transitions, not from statistical point?
Yeah, this is kind of one of the things that is, well, fortunate and unfortunate. The phase transition only makes sense and happen in the statistical limit. So basically, you really have to have a lot of things to see phase transition. And that's why, here numerically, to see a phase transition, you would have to see lots of particles. And in that limit, you would see that there is a sudden change in the behavior of those particles. You cannot have phase transitions with one particle. You need many. It's only a thermodynamic concept. That is actually, to be precise, you actually need an infinite system to really see discontinuities in the free energy. But if we just want to see sharp changes, not exactly discontinuity, the system has to be large and it has to be some kind of statistical limit.
Okay.
Sure. All right, other questions? All right, so let me know.
So in some sense, I think you mentioned renormalization group. So this is sort of similar to what I've seen where they mapped renormalization group theory to feed-forward networks, in the sense that the networks are coarse graining with each layer further and further, like the irrelevant statistics of the input.
Yeah, so
but it seems like you're extending this more generally to like something like where you have different organisms and they can interact somehow. So
right.
Yeah, very interesting.
Yeah. So to connect it to this RG flow with layers, it is straightforward, right? So you just have different layers, they coarse grain different information, especially convolutional layers are very close to that. Now here we actually looking for the RG flow of the completely unconstrained network, and that RG flow comes not from your architecture, which you design in a certain way, but from the change of rates of how the variables change and what they do. So it's in this sense, it's a generalization of the RG that you get when you predefine your neural network. That's one point. But the second point is you do get this different type of phase transitions that kind of very unique to biology. So I don't think there's anything similar to that phase. It's separate. So phase transition should be phase transition. RG should be RG. This type of phase transition is very unique to biology. I don't think you have any examples in physics where the correct ensemble is actually you have to average set a constraint on the log of the number of molecules. So I don't think. There is something that resembles that, but not quite. Yeah. But it is very connected to the RG in physics. Other questions?
Okay, and then also I think maybe I missed this, but so there's obviously the observable variables that are very fast changing, and then you also have like core that are very slow changing, like genome versus phenotype. So is that just a product of learning dynamics, where you have naturally them just appearing?
Yeah.
Where you have variables that kind of change quickly, like us learning, versus something more long-term like our genome?
Yeah, so very good. So question, would a generic learning system upon learning produce this range of scales of slow variables, fast variables, and intermediate. Well, we saw that. This is what self-organized criticality is, right? So we've had this already before. We've seen that learning favors spread of the scales. Now, but here it's something else. There are also gaps in those scales. So there is a cell, there's nothing in between, and then there is multicellular organisms. There's nothing in between, and then there is a group of organisms. So those gaps, an appearance of them is less clear. So again, we have observational evidences that it should be. We haven't seen numerical proofs, or even that this is phenomenology. We explain what we observe and we say here is a statistical ensemble that does that. Now, actually showing having a learning system that goes and develops the scales and then gaps between the scales and the new scales that we haven't seen yet. And that would be why it would be important. It would be like simulation of the origin of life. So yeah, I talked about this phase transition. I didn't call it. This is original life phase transition. And so here is a phenomenological model of how this happens. What is missing is a microscopic model. Here is your simulations. You had some, cars driving around, autonomous particles, and boom, all of a sudden they started behaving as organisms. So that phase transition from non-living and non-interacting to minimally interacting at the level of the microscopic simulation was not done. And that would, if one can do that, that would be a declaration like, here it is, here's a simulation of the origin of life phase transition.
Yeah, that sounds very interesting. Actually, that's very similar to, I think, what the argument neuroscientists claim, the ones that study the vision system, where they actually train the convolutional neural network, and then they say, oh, here's the receptive fields that basically look very similar to what we find in actual brain cells. And they're basically claiming, oh, so we have a model that reproduces experimental evidence.
Yeah. So, but that's now you're saying something more general, not just the original phase transition, but any phenomena we observe in biology. Presumably, we can model it as some effective algorithmic feature of a learning system. And if so, let's show that that is beneficial for which learning task, right? And then you would be mapping to a given phenomena to actual microscopic loss function, showing that it's beneficial and showing that it's where it should be used in the machine learning theory.
Yeah, I think it's similar in the sense that you have emergence of the receptive fields, just like we see it in biology. And here you have emergence of these slower variables. So the multicellular, more complex sort of life forms emerging from just learning, as we see in like biology. Right.
Yeah. So yeah, I didn't mention this. This is the first type of phase transition, which from non-living to living. But as Vladimir said, there will be a second one. And many more from unicellular organism to multicellular. Again, you already have cells that have shared degrees of freedom, but all of a sudden they now form multicellular groups of cells that we call multicellular organisms that start behaving differently, and they figure out that it's for their advantage for different cells to have different roles. That's another phase transition, and presumably all those phase transitions can be studied at the level of statistical ensembles and or numerically, simulated numerically, and that's certainly a very interesting direction to explore. Okay, well, thank you very much. Let me stop the recording.